I think everyone has been able to join. Well, it might be a few more people coming in, but let's get started. It's just the top of the hour. Just want to wish you a very good evening. My name is Joy Johnson, and I'm the president of Simon Fraser University. I want to begin today's session by starting us off in a good way. And it really is my honor to invite Elder Margaret, a member of the Squaxin First Nation, to offer a traditional welcome.
Thank you for taking the time to come to this very special event. And welcome to the territory of the First Nations people, Coquitlam, Musqueam, Squamish, and Tsleil-Waututh. Just a very quick prayer for each and every one of you. Great Spirit, thank you for bringing us together today. Just guide each and every one of us, taking care of us, our families, and thanking the communities from which we come from and our families for allowing us to do the work that we do. I ask Great Spirit just to bless each and every one, especially the young children who witness what we do and what we say, and just a very special blessing on all the guests who are present today, all my relations, and thank you for inviting me.
Well, thank you very, very much, Elder Margaret, for the wonderful welcome and your words. I want to acknowledge that I'm privileged to be speaking to all of you today from the traditional unceded territories of the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam people. It's a pleasure to be back at this President's Faculty Lecture this year with Dr. Stephen Holdcroft, who's going to be addressing us shortly on plastics, basically. As many of you know, the President's Faculty Lectures are part of SFU Public Square. And it's a signature initiative of our vision to be Canada's engaged university. By providing you opportunities to hear from and engage with leading researchers, these lectures are designed to enlighten and promote dialogue on important issues of public interest. This series of 6 lectures is exploring the theme of resilience and recovery from a variety of disciplines. I think it's a really fitting topic for our times and a great way for us to share ideas and to connect. That's why we're using the Zoom meeting format today. We feel it provides more of an opportunity for connection than a webinar format. It allows us to see each other on camera, so should we so choose, and to communicate through the chat box. So please feel free to introduce yourself in the chat now and let us know where you're joining us from. There'll be a chance to raise questions and offer comments after the lecture. And I encourage you as well to use the chat box during the lecture to post your questions and comments, and we'll be collecting them, and I'll be using them and posing them to Dr. Holdcroft toward the end of our session today. I want you to note that we have closed captioning available, and you can click the CC button at the bottom of your screen to activate closed captioning if you require that. I also want to note that this lecture is being recorded and will be available on the SFU Public Square website and YouTube channel. I also just want to remind you that we have community guidelines, which are posted on this slide as well as in the chat box. And just like to remind people of those guidelines. So now let's move on to the main event. Let me introduce Dr. Steve Holdcroft. Dr. Holdcroft is a professor of chemistry and a Canada Research Chair. He's the former departmental chair and president of the Canadian Society for Chemistry. That's a lot of titles. He researches materials for electrochemical energy conservation and storage. He's the author of more than 300 peer-reviewed articles, several book chapters, and numerous patents. And he's the recipient of SFU's Excellence in Teaching Award. With 3 former students, he co-founded the Vancouver-based Ionomer Innovations Incorporated. This is an SFU spin-out commercializing materials for clean energy. For services to the community, Dr. Holdcroft has received the Macromolecular Science and Engineering Division Award of the Chemical Institute of Canada, and the Canadian Society for Chemistry's Rio Tinto Alkyne Award. In 2018, he was the recipient of SFU's Outstanding Alumni Award for Academic Achievement. I'm really looking forward to this lecture. I was just saying, I find these lectures so interesting. I always learn something from a different field, and the variety's just been spectacular. So tonight we're on to plastics. So with no further ado, over to you, Professor Holdcroft.
Well, thank you very much. Let me just share the screen here. Choose the right one. Let's get into the slide mode, and I will use a pointer, and I'll try and keep my pointer from moving around too much. Well, thank you very much and good evening. It's a real pleasure to be able to talk to you on this lecture series on recovery and resilience. I'd like to talk to you a little bit about plastics, the good, the bad, and the ugly. But I'd also like to talk about the environment and climate change, which is simply bad and will be very ugly. And plastics have had a bad rap over recently because of litter and the propensity that we see around us. But I'd like to explain to you and show you that our future actually relies on plastics, and our ability to recover from climate change definitely will rely on plastics and future discoveries in this area. And in fact, one of the first uses of plastics was to avoid an environmental catastrophe. So back in the 1850s, one of the most popular pastimes was billiards. Billiards is the precursor, of course, to snooker and pool. And billiards required billiard balls, and these were made out of ivory. And the ivory came from tusks, and thousands upon thousands of elephants were slaughtered, really, for their ivory to make billiard balls and piano keys and ornaments and so on. And so there was a challenge to invent a material that would replace ivory. And that was one of the first plastics ever discovered. It was a celluloid. It was basically a cellulose, which is based on cotton, which had been nitrated to make celluloid. And some of you might have heard that term before. We don't hear it very often now. This particular material actually had ground animal bones in it. So it was a composite. And it had three main attributes. One, it could be made in mass scale. Two, it was cheap. And three, its properties were actually better than the original material ivory. And so we see that in plastics, properties being better than often the original material. And this saved thousands upon thousands of elephants, probably saved them from extinction. Plastics actually come way before that. Rubber trees, you can tap the sap of a rubber tree and cross-link it and use it for various purposes. But it wasn't until the mid-1950s, around the middle last century, where plastics really came to the fore. And it came to the fore because of some really good chemistry advances in catalysis, Nobel Prize-winning discoveries, and now with cheap resources, oil and methane and fossil fuels. We simply can't live without plastics these days. We see them in medical uses or PPEs. Take a look around your home and look at all the plastic parts that are around. And I'm going to use plastic and this term polymers interchangeably. But what you might not know is plastics are an integral part of computers. I don't mean the casings or the screens or iPhones and so on. I mean, we need plastics to image the millions and millions of transistors and capacitors that allow us to do our computing. Without the advances in plastics, we wouldn't be having this conversation right now. There would be no computing as we speak. And of course, we see plastics for lightweight and friction and so on and so forth. So I'll try and keep chemistry to a minimum, but I do have to give you an indication and give you an idea why they're so important and prevalent. And I'm going to start with one of the simplest molecules, methane. It's got one carbon, four hydrogens. You pump it into your homes, you burn it, it converts into CO2 and water. It's a gas. And you can add carbons onto methane. You can make ethane, propane, butane, that's lighter fuel, all the way up to octane, that's 8 carbons. That's gasoline, we combust that, that's a liquid. We keep going, we go up to 20 carbons long, we're now into waxy solids, candle wax. Well, what happens if you have 10,000, 20,000, 100,000 of these carbons strung together? Well, if you stretch them out, you would have extremely, relatively long chain. Relatively long because they're super thin, so thin you can't see them, a couple of nanometers in diameter. And even if you stretch them out, they would only be the width of a human hair, say. But they're hardly ever stretched out. They're always tangled, a bit like fishing wire, except can you imagine like millions and millions of different fishing wires all tangled together? And this is what gives them their resiliency. You can stretch them, pull them, you might elongate them, you can soften them, and it gives them fantastic properties over small molecules. Now, on top of that, we don't just have to have carbon hydrogen plastics, we can start to add other groups like methane to make propylene. We can put a chloro group on there to make PVC, polyvinyl chloride, benzene groups, polystyrene, fluorine groups, Teflon, and I won't go through the myriads of different types. But you can also start to insert different atoms. You have to think back to your chemistry if you're not a chemistry. Nitrogen, oxygen. Now we get into amide bonds and very strong bonding between chains, very high performance polymers. And every one of these polymers is made differently and they cost a lot differently. These will cost a lot more than these, say. And when you try to recycle them, you've got a problem because they're not the same. We have to stamp them with different numbers so you can package them and we can try to isolate them and recycle them. And so chemists have been a victim of their own success. We were asked to make materials stronger, harder, faster, cheaper, and we did that. Replaced cement, replaced wood, replaced glass, ceramics, to the point where the uses of plastics have just been growing and growing. And these are millions of tons of produced per year projected. This study came out in 2013, predicting gigatons, that's 10 to the 9 tons of plastic per year to be produced. We're sitting here now, 2021, projected to be over 400 million tons of plastic produced. That's exactly where we are. We're right on this path for producing large amounts of plastics. And in fact, in the last 15 years, we've produced more plastic than we have done in our entire lifetime. So you can see the size of this. Now, the difficulty becomes in recycling and capturing this. And so a lot of this ends up back on landfills, even though we recycle them. And landfills contain about 10 to 15% plastics. We have other problems. Many landfills are designed not to decompose. So many of these constituents are not decomposing. But plastics, we know they often float. And so we tend to see them accumulating in oceans, the size of islands, small islands. We see them on shores. They're an environmental eyesore and a disaster. And we really need to stamp this out. So that's the ugly. The positive side is every country, G20 country recognizes this. And they recognize that in throwing away plastics and landfills, we're throwing away valuable material. And in fact, we're throwing away billions of dollars of material that we can actually use. And so this has caught the attention now. I should say maybe the environmental aspect has, but certainly economics. We spend millions of dollars throwing away billions of dollars of material. And so that's an incentive to get this back. G20 countries have got different mandates to take back this plastic, but it's not easy at all. It's quite difficult chemically and technologically. What we have to do is, well, we start off with small molecules. We string them together in chemistry. We use them. we need to have a method to get back the original material so we can have something called a circular plastic economy. And if we have mixtures of plastics, I just told you they come with different chains, different types. Well, we need to be able to separate those different types, because we can't have polystyrene in automobile cars and so on and so forth. We need the right type of material for the job. And so these technologies are coming to the fore, but they're way, way behind commercial viability on large scale. And that's because this area of science needs research. It needs hardcore research at the chemistry and at the chemical engineering level to address this challenge of getting our materials back and reusing them. This is the only way we solve this problem. We have no off-the-shelf problem solutions right now. But you may be surprised to learn that we actually take plastics and we burn them. That's because plastics are large chains of carbons and hydrogens, and if we combust them, we get energy out of them, just like we combust gasoline. And so some countries take about 50% of all their garbage and they incinerate them, and they get the heat energy out of that. And they use that heat energy to make steam, to drive turbines, and then electricity, which goes into power homes. And you might be surprised how much that happens. I can't see this because it's blocked by people on my screen, but I do know that the amount of incinerated plastics is increasing. But of course, you've got to take out all these nasties that are coming out of the effluent, dioxins and furans, which can be done with only 99+ efficiency. What you can't take out very easy is CO2. So this is where I'm going to transition to CO2 and climate change, because surely we don't want to be burning plastics, even if we're getting the energy out. And we don't, not straightforward, we don't. So let me move to CO2 emissions and greenhouse gas. CO2 is the greenhouse gas that's in topic right now. Carbon dioxide is in our atmosphere for sure, it's always been there. But once we hit the Industrial Revolution, we started to emit CO2 in unprecedented quantities. And we talk about this number, parts per million of CO2. And we're now sitting at around 400, which is very high. And I'll show you the impacts of that shortly. If there's CO2 in the atmosphere and it's increasing, CO2 is going to dissolve in our oceans. Think Coca-Cola. We gasify drinks with CO2. CO2 is slightly acidic, so what it does, it lowers the pH. Think back to your high school chemistry. It makes the oceans slightly more acidic. Who knows what's that going to do with the oceans? Well, some people do know what it's going to do to the ocean. The CO2 that goes in the environment doesn't go anywhere. It sticks around for hundreds of years, maybe millennia. We're simply slowly increasing our CO2 emissions. Now, what effect does this have? And some of you might have seen plots like this before. It's a very busy slide, but you can see simpler versions, but I like this one. These are our CO2 emissions every year. And approaching around 2015, there was a big meeting in Paris, the Paris Accord, where we needed to decide we need to do something. If, as a society, we continue to spew out CO2 emissions without consequence, we are projected by the end of the century to increase the global temperature between 4 and 5 degrees. Okay, you may not think that's warm. It's pretty warm. I'll show you how warm it is. If we can keep to the pledges that were made at the Paris Accord, we can keep the temperature rising. We can stabilize the CO2 emissions as what they are now. We can keep the temperature somewhere between 2 and 3 degrees. Now, what does 2 and 3 degrees give you? Well, that global warming is not a simple 2 degrees all the year round every single place. It is spatially differential, and it is also temporal, meaning some places are going to get warmer for larger periods of time, and places like the Arctic are going to be 10 degrees hotter in their coldest temperature, which means ice caps melt and so on and so forth. But what does a global temperature 2 degrees rise for us sitting in Vancouver, for instance? Well, the closest data I could find is in the hottest days, the temperatures will increase by 6 degrees. So if you think forest fires are bad now, in the last few years, wait another 10, 20, 50 years. And if there are any forests left to burn, they're going to be very substantial. And so this is having a huge impact in the way people are thinking about this all over the world. And this is why you're seeing a lot of this in the news right now. I can't go into this slide. Please, if you get time, can have a look back, or I can email you this link. A 2 degrees increase tells you what's going to happen. And it allows us to look at scenarios. What if we can keep our temperature to 1.5 degrees increase? And this ½ degree increase saves us a tremendous amount of pain and suffering. And so it turns out we need to get to lower the global warming to 1.5 degrees. And that means we can't just keep our CO2 levels constant. We have to reduce our emissions to zero and keep to that pledge and those policies. We need to get to zero net emissions by 2050 in order to keep our temperatures to just a 1.5 degrees increase. So that's where currently we're sitting right here. We're looking at a 3 degrees. With the pledges, we're looking at 2.4 degrees. If people get serious, such as the emissions announcements announced in the last few weeks, we could keep to 2 degrees. We need to be 1.5 degrees to keep this. How do we do this? Well, I'd like to say simply, but it's not simple. We do, but it is possible. One of the ways to get to low CO2 emissions is to move to a hydrogen economy. That is moving away from fossil fuels and the burning of carbon materials, and instead burn, whether literally or otherwise, hydrogen, and get the energy out of hydrogen as it gets converted into water. Because that's the product. When we heat hydrogen and burn it, we get energy and we produce water. Almost every G7 country on the planet has a strategy to move toward a hydrogen economy over the next several decades. Canada came out with its hydrogen strategy just last Christmas. Most of the countries came out in the last 1 or 2 years. This has been around a long time, but now governments and the funding agencies and the policies are starting to recognize that we're heading for an absolute catastrophe if we don't move into a greening of our fuel sector. Now, I'm not going to go through all these, and I'm happy to share links if people are interested. But what does a hydrogen economy mean for Canada? Well, it means by 2050, more than 5 million hydrogen fuel cell electric vehicles. It means 20% or 30% of our energy comes from hydrogen. It means fueling of hydrogen all across Canada. And we could point to many other countries and they would all have massive numbers like this. So how do we get from where we are now to 5 million fuel cell vehicles on the roads? Well, now I have to give you a little bit of science, take you back to an old high school experiment where we know that if we take 2 electrodes and we immerse them in an acid and we pass electric current, we split water. We take the chemical energy of a battery, convert it into electrical energy, And that energy gets put into water, splits water, and that energy is now stored in hydrogen. We know that if you combine hydrogen and oxygen, you can get that energy back. Remember the Hindenburg disaster? That's a whole other story. But it's much cleaner if you can do the reverse of this. What if we can have two electrodes and bring hydrogen on one side, oxygen on the other side, keep the two gases away from each other, do a reaction, will oxidize hydrogen to protons, H+, which is an acid, and the protons have to move through to the other side where they combine with oxygen to form water. Where do the electrons come from? Well, we make them go through a circuit. So this is where we tap all our energy. Now, this has been known for hundreds of years. And in fact, it was used in the Apollo missions. You might remember the Tom Hanks movie where they were all in peril due to a faulty fuel cell. Now, the fuel cells don't power this part. They power the auxiliary power to keep life support systems. Now, those systems had an acid, and that was a hot boiling acid, 180 degrees. Nobody wants to be pumping around hot boiling acids, especially if you're operating in closed environments. So the advancement here, and this is where I'm trying to bring this round to the title, the advancement in this technology came in the form of a plastic, a very special plastic, one that costs about 10,000, maybe 100,000 times more costly than your plastic bags, but a plastic nonetheless. It is a Teflon, and attached to that Teflon molecule is the acid group, the sulfuric acid. So this is a super strong acid. It's like sulfuric acid, except this one you can lick, you can chew on it, but it's still a strong acid. And it conducts protons like an acid would. Now, for electrodes, we spray coat on either side of this plastic super thin layers of a catalyst like platinum, what you would see in a catalytic converter in a car, same material. And so you end up with a very thin sheet of plastic coated with two electrodes. And what we're doing, we're bringing hydrogen on this side and oxygen to that side, connecting the electrodes and allowing current to fall. Thickness of this, about a fifth of the width of a human hair. So this is the advantage. This is the technology that's going to help us. This is what's going to replace the internal combustion engine in principle. So simple. I'm going to focus on the plastic. Another person might focus on the catalyst layer. Another person might focus on the engineering. But you need plastic, you need thin coatings of platinum and lots of it, expensive. You need flow field plates to bring hydrogen in, oxygen in. You're generating water, you need to get that out. You need current collectors. Now, if you did this like a letter-sized sheet, you would get pass current and bring hydrogen and oxygen, you would get about 240 watts of power. What's 240 watts of power? Think of your light bulb, about 4 incandescent light bulbs. And so that's the scale we're dealing with on an A4 size, a letter size sheet. What do we need for an automobile? Well, not 240 watts, we need 80,000 watts of energy. That's 80 kilowatts. And you start to see the magnitude of the problem now. We don't just want one of these little pieces of plastic. We need hundreds and hundreds of them, all put together, all engineered very tight so that there's no gas leakages and so on. Well, that means we need hundreds of membranes. If you want to do this for millions of cars, literally millions of cars, you're looking hundreds of tons of years of a new plastic and millions of square meters of plastic. So this is the challenge. This is why plastic is the bane, yet it's also the solution. And this is an area of research we're involved in at SFU, and I won't go into the details of this one, but there are problems with this plastic because it's based on a fluoropolymer, which has some environmental concerns. And our contribution to this is to move away from fluorous materials, fluoropolymers, into non-fluorine. That for another day. Anyway, we can make fuel cells like this. They're put in stacks. You may have heard of Ballard Power Systems. That makes literally tens and tens of thousands of these. They go into cars. There are thousands of cars on the road all over the world, and tens of thousands of fuel cells in forklift trucks and so on and so forth. To power these, you need hydrogen. And this is the next piece of the puzzle. Where are we going to get all this hydrogen from to replace gasoline in the future? Right now, what we want hydrogen on corner stores. We want to be able to fill our cars and fill whatever you want to fill with them to use hydrogen. Right now, the hydrogen comes from steam reform of methane, a fossil fuel. You take methane, you treat it high temperature with water, you get hydrogen, but you also get CO2, and lots of it. So CO2 is being emitted into the atmosphere. Ideally, and we're going to have to do this for a while, there is no quick solution to getting hydrogen. But in the long-term future, we want to get our hydrogen from a clean source. We want to get it from electricity. How do we do that? Well, think back to that original high school experiment on a massive scale. Where do we get the electricity from? Well, we get it from wind turbines, solar power, hydro. Why can we start thinking about this now? Well, 10 years ago, there weren't that many renewable sources on the planet. But in the last 10 years, renewable energy has been growing leaps and bounds, and the cost of electricity has been dropping for renewables. So now we can get a cheap source of electricity. In fact, this technology has been around for a long time, and some countries rely on it, especially countries that have cheap electricity. Why do you need cheap electricity? Well, you have big resistances between electrodes and getting it through a porous separator to drive this reaction. Moreover, you need to do this reaction in very caustic solutions, not acidic, but caustic solutions, very basic. And basic solutions are very nasty to work with, but you can do it. You can stack electrodes by the hundreds and have a very big, like an airport hangar, to make hydrogen. This is done today, but you won't see it around in every major country. What we really need is to move away from this large scale liquid electrolyte, heavy electricity consuming, large capital cost process. We need to move to a system that involves membranes, just like we see with fuel cells. Imagine a membrane that could transport ions, very cheap catalysts, pack them tight together into a little few stacks and cells. And now the footprint of this hydrogen generator becomes a lot smaller and a lot more cost effective. Modeling studies show that by doing this, you can reduce the price by a quarter, by a third, or up to the half the amount you would normally do. Now the energy companies are interested because you can make hydrogen cheaper from the electricity than you can from methane in the future. So why can't we jump on this right now and replace all our sources? Well, the stumbling block in this process has been the membrane, because I've mentioned that we use caustic solutions in these technologies. That means we have a hydroxide ion. And some of you have used this at home. It's in Drano. It's what we use to clean all that gunk out of drains. The organic materials are eaten away by caustic solutions. So this presents a problem because until recently, there was no plastic that could survive these caustic solutions, because these plastics have to be made with dependent groups with positive charges, cations. And so the cations can help transport a hydroxide ion from one side of the electrode to another. 10 years ago, if you asked me if this was impossible, I would say absolutely not. We clean our glassware that we make plastics from in caustic solutions to dissolve in the way. So to make a plastic that's stable would be inconceivable 10 years ago. But that's what we've done, and that's what others are doing around the globe. We took a plastic called polybenzimidazole, which is itself a high-performance material. It's used in spacesuits, fire extinguisher suits. There are carbons here, if you're not a chemist, very strong material made by the ton. And excuse the chemistry, but I have to show this, but we do what we were planning to do, and we discovered this serendipitously using very simple first-year chemistry. We want to alkylate at this position. I'll just draw a small unit here, and alkylate at this nitrogen. And when we do this second alkylation, we get a positive charge in the backbone. We have an anion, which is an iodide in this case. And so if we can do that to this polymer, we make a polymer with positive charges and mobile anions. We want to exchange the iodine for OH minus. Well, we can make this. We made this for the first time. How do we get the iodide ions out and replace it with OH minus? We simply immerse it in caustic solutions. And when we do that, the polymer disappears. And it never comes back. It actually degrades and decomposes, which happens to the thousands of other materials like this that have been tried. But what we do as chemists, we find out why it's decomposing. And for you chemists in the audience, I'll tell you it's because OH minus is attacking at this, what's called a C2 carbon. That is the most reactive spot. And when it reacts here, then it ring opens. So we want to solve that. And we solved it by putting groups onto the contiguous phenyl group next to the C2. We did some steric encumbrance, which is standard in the drug industry and other areas. I'm not going to go into that chemistry. I'd spend hours talking about that. And we made some advances where in caustic solutions at 80 degrees, we started off with very low lifetimes, a simple modification we got into weeks of lifetimes, and through increasing the stability and understanding of basic research, and hence the title of the presentation, we were able to get materials which are highly stable. So in the lab, we make small batches, maybe grams, 5 grams. We obtain funding to scale up to 1 kilograms of this material, literally bucket chemistry, polymers that look like this. But we need to start to move into the tens of kilograms. And if we want to really tackle the hydrogen problem and make clean hydrogen, we need to make hundreds of tons of this material. So enter SFU again, and through the SFU BD School of Business, and with Ben Britton, who took an engineering degree with Alicia Main and great assistant to spin off, with Ben and Tim Peckham students and another student, Tij China Vessen, where the four of us spun off this company to scale up. Now, academics in this arena is a very difficult environment. We got a lot of advice from our board of directors, Chris Bissonnette from Palasite Funding, and Jim Derbyshire, who's a friend of SFU and a former Chancellor Award winner of SFU, have been instrumental in launching this, as our new board of directors, and Bill Heberlin we brought on as a senior CEO, who has now led this company to the production of hundreds of kilograms. This company is now manufacturing these kind of membranes and working with the largest group of energy producers in the world to try to implement this technology. And this technology is being incorporated and is the foundation for a lot of the hydrogen technologies that we're going to see in the future. So many kudos to them. So I could end there, but if I did, I would be remiss in one important point. So bear with me a couple more slides, a few more slides. This is Canada's path to decarbonizing our future. We're typically emitting 700 millitons of CO2 a year. And that's what we would do if we didn't do anything about it. If we are responsible and we decarbonize the electricity, that means we become more efficient in our homes and industry. We can reduce our CO2 emissions substantially by a third. If all goes well with the hydrogen technologies, we can roll out the fuel cells and we can roll out producing hydrogen cleanly, then we can start to really hit into way to the CO2. That still leaves, by 2050, about 100 millitons of CO2 we're emitting. We need fossil fuels for some things, materials. We're just one country. Other countries will be kicking out a lot more than this. And in the meantime, over these next 30 years, we're putting CO2 into the environment. And remember, it's not going away, it's accumulating. It's sticking in the environment. So even though I've given you these positive outlooks, the future is very, very dire unless we can get to this part, unless we can really reduce to net zero greenhouse gas emissions. So this is why I'm so positive. You may have heard the word carbon sequestration and capture. And when I looked at this cartoon and looking at CO2 emissions being captured in fans stored underground, and as cartoonish as that may seem, this is what the plants look like. Literally separating the CO2 out of flue gases and pushing them underground in various forms of carbon. Now, they can stay here from whence they came. That's where the methane came from in the first place. Or we can accumulate and do something with it. And this is going to what really affects the planet in the future. In the last 10 years, advances, particular Canadian advances, U of T, University of Toronto and UBC and other places, and now us at SFU, taking that same electrochemical technology with energy from renewables and configuring these electrochemical stacks so that we don't produce hydrogen, but we take CO2 and we electrochemically reduce CO2 into higher value products. Carbon monoxide, which is a feedstock, C2H4, ethylene, which is the building block for polyethylene and most plastics on the planet. And so this is technology that's developing very rapidly, taking CO2 and converting it into natural gas, circular economy, into plastics, and so on and so forth. This is super exciting, and it will revolutionize. We can take the CO2 that we're capturing and storing, convert it into fuels. What does it need? Well, it needs a membrane that can operate in caustic solutions. And right now, there are just a handful of those, modestly say, the ones that have been invented at SFU and are being scaled up for large scale, because this is a large scale, this isn't a lab scale problem, this is a mega scale problem. Iono Innovations is one of the countries making membranes to develop that. Of course, we need catalysts, a huge area, and we need engineering. So I'm going to wrap up here. I'm going to tie in the plastics development with the CO2 emissions. We've been increasing our CO2 emissions gradually. We cannot continue to do this. We need to reduce And this particular time around the pandemic and lockdown, it's just made us all very reflective of the future. And so right now we're starting to see major players around the world in G20 countries making strong efforts to address the CO2 emissions and at the same time address plastic waste. So I started off with how plastics came to the fore to ward off an environmental tragedy, which it did. Some of you might remember the Graduate movie with Dustin Hoffman, where he was taken aside after graduation and told one word about the future. That word was plastics. It certainly became the word for the latter end of last century, and it will be the key to developing our future. We do have to keep an eye and start to develop new plastics so we don't have plastics in the environment. But I'm convinced, and many other people are convinced, that this membrane-based technology will allow us to clean the environment, and it will allow us to move from a CO2 carbon technology to a hydrogen technology, and eventually convert the CO2 back into a useful fuel. So I do thank all the members of the group who keep me motivated on my toes and an inspiration for all the ideas that come out of the group. And there have been literally 100 people, hundreds of people that have come through that research group. Very strong depth of thanks to all the collaborators in physics and in chemistry, and a huge number around the globe. The Department of Chemistry and Faculty of Science, and in fact all the levels of administration have been extremely supportive of the kind of work that we've been doing and this movement in general. Very thankful for that. As our very strong collaborations, Ballard Powered Systems, we've been working with for 25 years, National Research Council Canada, National Research Council of Canada, Canadian Hydrogen Fuel Cell Associations, and more recently, this 30-person strong company, I&M Innovations. I can't stress enough the importance of research and development. Without the basic funding from federal and government agencies, we can't do this. Nobody can do this without basic research. We can't make a dent into what's going to be a massive problem if we don't deal with the CO2 emissions in our environment. So I hope I've left you with the sense that we have a problem, but we have a solution, and that solution relies heavily on research and advancements that are taking place in Canada and indeed at SFU. So with that, I'd like to thank you for all your attention.
Well, thank you so very, very much, Professor Holdcroft, for your presentation. I really enjoyed it. I actually followed that chemistry. You are a very good teacher indeed. So thanks for, walking us through that and showing us some really interesting connections between carbon capture, the future of hydrogen fuel cell technology, and indeed the connections to trying to keep our planet, the temperature not rising. So thanks for all of those connections. Really nicely done, and I really appreciate it. There are questions already in the chat and comments as well, and we'll get to some of that. But I'm going to begin. You really do seem to be one of the more optimistic people that I've heard speaking about the possibilities of the future. And obviously science seems to be very much a part of that. So I'm just wondering if you can just comment on your optimism and why you seem to think that we are going to be able to crack this nut and figure this out as we move forward.
Yeah, well, thank you. Yeah, thanks for the opportunity. Well, deep down, I'm very concerned about the dire consequences we're going to be in. But optimism because I can see a path forward from a science point of view, and not just hyperbole, we've got to do this or throw money at this. But I've actually seen the science and technology that can get us out of this if we're willing to make that step and invest and take it seriously. And optimist because 10 years ago, I have to be frank, I couldn't see that door for us to get through, particularly with the CO2 emissions. The hydrogen, yeah, I could see us developing that. Could I see how much could we produce hydrogen on scale 10 years ago? No, but things happen, things change. And what happened was all this renewable energy came about. I don't want to say out of nowhere, but the cost came down considerably. And so much so that people were starting to ask, well, how do you store all this excess energy from the wind when, or from the sun? Because you can't just turn these things off. You have to keep pulling the energy out. In fact, in some countries, you have to pay to put energy back into the grid when we don't need that much. So I saw the optimism of all that energy, as did many. And then the breakthrough I saw with these alkaline membranes, which I'll be frank, I could not see a solution to this chemistry 10 years ago, 15 years ago. In fact, I was very critical, saying there's no way, because you can't make a plastic that conducts caustic and is stable. It's just fundamental. And since then, discoveries like what my students have made and others around the globe, just complete eye-opener. Now it's a question of scaling up and moving that. And so I'm optimistic, not just because the governments are taking notice, because there is a future technology which needs to be nurtured and can have a massive impact on this.
It really also, I love that science, or plastics basically, because it does show the importance of basic science in terms of really moving the fields forward. So it's a great example. One question I had is, in terms of fuel cell technology, are we going to run into a similar issue down the road in terms of dealing with the plastics in the fuel cells themselves? Or you talked about that virtuous cycle in terms of the energy system, but what about the plastics involved?
Yeah, you're absolutely right. We will indeed. Are people paying attention to it now? Yes, but only small scale, because we haven't seen the kind of rollouts that catches the attention of funding agencies and big business. And you did mention one, and this issue with the fluorinated materials is an issue that's going to come and bite us really hard. But there are solutions out there, and that can replace the fluorinated. There are issues with platinum, for instance. How much can we get? But there's a lot of how much do we have around. The costs go up as it gets scarce. The cost of metals for electrolysis has gone up 100 times, maybe 1,000, because now we realize we're moving to that environment. Every time we push for a new technology, there will be hurdles. But I'm reasonably confident, knowing the activities around the world, knowing pretty much all the researchers in this field around the globe, that collectively, that's a problem that can be solved. The circular plastics problem that I talked about at the beginning, that's really at its infancy. That needs a lot of work and a different mindset. We can only solve that through some basic science and then adoption. And it is a problem. It's not as big as a problem as the climate change, in my view, but it's a problem. Yeah.
It's interesting to me in terms of just trying to think down the road about the implications. And I definitely appreciate the importance of basic science and kind of going where discovery might take you. But do chemists also try to think through the ethical implications of what they're discovering and how it might be used? Is that something that
that's a good question. Well, you're touching on a very important topic. And here, see, like the kind of research we've built on, and what many people are built on, it's kind of doesn't have any ethical basis. It's built on a lot of simplified reactions and catalysis and structures, and how do you measure this? How do you measure that? How do you react this compound to other compound? And what we've done, we simply build all that, taken those building blocks and used them all together like Lego in a strategic way. But we can't, if we don't have those building blocks, which are less of an ethical problem, then we can't do what we're going to do. Those like us can't make these kind of solutions. So at some level, yeah, you have to think ethically, but that's more along the what we call the technology readiness level, further up the path, up the chain. Well, you know that term, of course. But at the basic level, basic chemistry level, physics and math, there's not a lot of ethics to think about.
Yeah.
But certainly, researchers like myself are getting more directed towards strategic goals, and that's good in one way, but it also limits basic research and the discovery. So we need all aspects. So
yeah,
that's a roundabout answer to your question.
Yeah, no, I appreciate that, and we've seen that time and time again in terms of solutions for society. It came out of discoveries that people never knew would lead to that particular solution. So yeah, no, I understand what you're talking about in terms of those building blocks. So, you talked about hydrogen fuel cells. You're really pointing us to thinking about a more sustainable future. So what advice would you give politicians, scientists, communities in terms of helping us think through how we're going to move to a more sustainable future?
Oh, yeah, that needs different levels of leverage. It certainly needs directions into research and technology, and so the only way we do that is for government agencies and governments to recognize the urgency and the importance of basic and strategic research. That will take, how do you do that? Well, it takes a lot of lobbying, because I know people making these decisions are getting information from many different sources. And who do you trust? But I would urge people to read up about the climate change and go on to the United Nations studies. But sustainability, we can't get there right now with our current technology. We're not in a position to say, okay, this is a solution, let's deploy it at scale. There needs to be a lot of work done. So that's one. To get the sustainable future requires research. And after that requires development. And so we need to get that going right now, and we need to have it recognized. I think recognition is that we have a problem. Is the first part of this problem we've got to solve.
I'm also kind of curious about the infrastructure side of things as well. You talked about the scale up to produce the hydrogen, but ultimately distribution of hydrogen, like just think of how difficult it's been to get charging stations for electrical vehicles across this country. Like there's also a whole other side to this, isn't there, to think about?
Oh yeah, absolutely. There's codes and safety. If we didn't have gasoline stations on every other block, in this climate, this day I should say, there's no way we would be able to be pumping fuels of that quantity. It's probably unlikely we'd be pumping methane gas into our homes if we had to start from scratch. But we do, and we do it safely. So there's that whole area of codes. There's this whole transition from fossil fuels into hydrogen, and recognizing it's not an and or, it is a transition. We do rely on fossil fuels, and we will rely on them for a long, long time. And these are difficult decisions, but a lot of investment has to go into the green side in order to get there for for 50 years, in 30 years by 2050. If we miss those marks, if we don't get down to zero emissions by 2050, we get it at 2075, we're at 2 degrees warming, no matter what we do. So there is some urgency in this, but it's solvable, I think, if we can train people in the right area.
I'm going to start to turn to some questions from the audience. I've seen a lot of comments. I'm starting to sift through those as well. And so I'm going to encourage people to post questions in the chat. I see, as I've said, you've done that already. I'm also going to encourage people to raise your hand. There's a reactions button at the bottom of your screen, and you can raise your hand. I see Connor has done that, Connor Brady. And I'm going to kind of go back and forth between some of the questions, and I'm happy to pose them. But if you'd like to pose the question you put in the chat, just raise your hand as well. For those of you, and I'll try to get to as many of these questions as possible. So, and if you are going to ask a question, if you feel comfortable, it'd be great for you to show your face. But if not, that's okay too. So, Connor Brady, you've got a question. I'm going to open it up for you.
Hi, yeah, thank you. I have a couple of questions. The first would be probably a quick and easy yes or no, but with the G7 or G20 community, is that enough? Is that enough commitment from those few countries or select countries to actually bend this in our favor?
Yeah, I think I have to say this isn't my area of study, so I don't study economics and various forms of climate change that detail. So I read just like everybody else, but my understanding is that the countries that are making new pledges account for like 73% of all the GHGs. And some of the countries that you think might be more polluting are actually working really hard to reduce that. So the answer to that is yes.
Okay, thank you. And then my next question is, from what I've read, feel free to debunk it, is a lot of the plastic pollution is within the ocean from fishing. And a lot of the ocean is holding, or holding basically a lot of CO2. With the pollution, it can start to release that. Is the effort for plastic cleanup basically, should that be spent on the ocean cleanup?
That's a good question. Someone would have to look at the economics of that. But I think I was talking about more of not an immediate challenge, but more of a moving forward into a long-term challenge of preventing the plastics getting out into various forms in the first place. And that's where people in my field can make an impact in the chemistry side of it. But you're right, these effects in the ocean are significant. If you've ever attended a talks about atmospheric chemistry, there are biofilms on the ocean that are being affected by changes in the CO2, and that means you get lots more release. And it's a way more complicated ecosystem than I can fathom, and it's one that needs careful study. But you can study it to death, but we do need solutions. And so I think we're going to try and move forward with solutions of keeping plastics out of the oceans. That tends to be a litter problem rather than a garbage problem and a recycling problem. So each of these has got its own little ecosystem to solve.
Steve, I'm going to move us on to a question in the chat. And this is a chemistry question, I think. Give it a whirl. If you power vehicles with hydrogen, well, maybe it's not a chemistry question, take it back. If you power vehicles with hydrogen, where does the water byproduct go? Does it just get released into the environment? Is the water clean, or is it fit for human consumption or use?
The water, great question. The water comes out of the tailpipe, just like the water does come out of the internal combustion engine. So if you've seen, I'm sure fuel cell cars have some way of maybe even storing it or moving it around and keeping it. But if you've ever seen a car take off after it's been standing, you'll see droplets of water. If you combust octane, you get CO2, you get water. If you combust hydrogen, you get water. And in fact, the early fuel cell buses were notorious for this, because on a cold day, you would see these huge plumes of what people thought were smoke coming out of the exhaust, and it was just water coming out of there. No more than is coming out of the internal combustion engine. Can you drink it? Well, if you could, that depends how desperate you are, I suppose. But they did in the Apollo missions, I believe. I believe they filtered that and cleaned it.
Interesting. I see that Jill Schroeder, that you have your hand up. I'm going to come over to you.
Thank you very much. I want to appreciate your combination of realism, science, and optimism, and that balance. I'm not a scientist or let alone a chemist, but I am part of the green team in my building. And my question might not be something you feel like you want to answer, but I thought, well, I do have a question. If you could name 2, let's say, changes that individuals could make going forward, what would you suggest?
Oh, that's such a difficult question. Well, it depends on whether it's going to be, it's a great question, Jill. It depends on whether it's going to be a short-term, and no, short-term is the wrong word, an effect that is demonstrable to others, so we can start to work together for a cleaner environment. So it could be, you know, if you're making an impression on a young child, for instance, of recycling and so on, that will have a lasting effect for their lifetime. And if we want to really have change, depending on where you are in the society, lobbying a politician would be a really good process. And to get to this idea where we can't put this off. I'm sorry, I'm just going to digress just a little bit. It's because it's really hard to think 2050. I'm not going to be around at 2050. I'm certainly not going to be around at 2100. And so you have to pinch yourself to keep reminding yourself that this is real, and even though it's not affecting us, it's going to affect somebody. So the single most event, I tend to look to the future now. For 2050 is a good year to look forward. So anything you can do that will get us on track for net greenhouse gas emissions for 2050, for me in the long term, has the biggest effect. And that might be as simple as getting people on board in this by recycling, or it might be lobbying politicians some way. Sorry, I can't be more specific.
Thanks. You know, it's interesting. There's a question in the chat that's just a definitional question. What does net zero by 2050 really mean?
Oh, sorry, great question. My understanding of this, and someone correct me if I'm wrong, it means that we are not pumping any CO2 into the atmosphere. We are collecting it, and so that it's, well, so we're not putting it into the emissions. Now we might, at some stage, we might be storing it underground, but that still counts as long as it's not going into the atmosphere. We can store it in the ground in different forms, in carbon. We have companies out in the West Coast and Squamish and so on. If the technology develops, we can take that CO2 and reuse it. That's the ultimate goal. That's what's exciting people. But it just means we're not putting significant CO2, greenhouse gas, into the atmosphere.
David Sanguinetti has a question. I'll go over to you.
Thank you. So, Dr. Holdcroft, I'm a chemical engineer, so I am a great fan of your chemistry. I think you're doing some really cool stuff. I am curious, though, on the, I'm a big fan of the use of hydrogen in applications and in a number of applications. I'm wondering why you're focusing on fuel cell vehicles when there's so much hydrogen currently being used, so much SMR hydrogen being used, whether it's for ammonia production or hydrocracking, making biofuels even. Would it not make more sense to focus first on cleaning up that, replacing that, the SMR, so-called gray hydrogen with green hydrogen before we go working on vehicles where, frankly, a battery electric vehicle is more efficient use of that recyclable energy or green energy, whatever you want to call it.
Thank you for that. And in omitting the uses of hydrogen in steel and cement and so on, which are huge, right? But
steel, yeah.
You can possibly imagine. In omitting those, it was simply, I've been told to keep within 35 minutes, and I talk about what I know about, and try to keep what I don't know about to a minimum. So you're absolutely right. The way we, if I understand it, the way we reduce a lot of those greenhouse gas emissions in the interim, in that first short term, is by doing exactly what you're doing. And we continue to use steam and flame reformation for producing hydrogen. That isn't, I'm not proposing we stop all that now and focus on cars. My best answer is I'm looking at 2050. That's where we want to be. And if we want to have all that hydrogen fuel cells by 2050, we have to start now. That doesn't mean we stop everything else. I mean, if we did that, we would be in massive trouble. The same with electric vehicles. It's not an and an or, it's not a competition. Electric vehicles have a place, and they will have a place, and they have no place in certain places, and same with fuel cells. And so I strictly focused on my area of expertise, which is in hydrogen and fuel cells, but you're absolutely right. It deserves to have another lecture on electric vehicles and the rollout of that, which has been absolutely critical, not just for the energy saving, but this mindset that we can actually move away from gasoline up our cars. We can actually use electric vehicles. I mean, that's a tremendous boost in our psyche of moving to zero emission vehicles. So completely agree with you, and thank you.
Yeah, it's interesting. That came up as well in the chat a little bit. This question, Steve, about you've spoken a lot about hydrogen. What about electric vehicles? And what are the pros and cons? And it seems to me some of it is about distance, I guess, and infrastructure as well. Those would be two. Are there other things that
it is a distance, and and it's fantastic. But in the, I would say in the long term, 30, 40 years, most of the companies that I know of, hydrogen is their long-term future, just because of the speed of filling, the quickness, the inexpensiveness of the hydrogen in 30 years, the disposal issues with battery. I mean, I don't want to make this into a battery fuel cell. They're both part of this solution, but I would say in the long term, because of the density of energy that can stored in hydrogen, the refillability, that's going to have a major role. And this is why countries are bending over backwards to roll out hydrogen strategies, not at the expense of electric vehicles. We need them, battery vehicles. We need them now, and we will need them in the future.
Thank you. Tracy, I see you've got a question.
Yes, hi. I guess I'm just listening to this really interesting forum. I'm not a person involved in science or recycling, but listening to what everybody's had to say, I guess my concern, I sort of tuned into this because I'm more interested in plastics, recycling in the environment. And I was given an invite through the Alumni Society just to sort of hear what was going on. And I think it's so interesting not being a scientific person, listening to all the feedback from all the people that are in science and how much information they have that shouldn't, when we roll out federal plans or international plans, work with different groups that are scientists and find solutions and start working towards this. Not eliminating, like there's been a lot of comments about hydrogen and stuff that I don't know anything about, but just listening to the comments that people have to say, it's almost interesting that we should be having people that are scientists and experts in these fields, because to come up to 2050, I'm really concerned myself about I won't be around either because I graduated in 85. I guess I'm concerned about really seeing what's going to happen in the future and what's going to happen for the next generations. And is our world viable the way things are going? And some of the things that the people in the chat and the people that were in this forum brought up, I think that the politicians and everybody internationally, I did have a conversation on the chat with someone about working together with the G20 nations, helping the poorer countries start recycling programs and start working on infrastructure for scientific technology to basically sort of alleviate all these concerns that were brought up. So I guess, I don't know what you can comment on that, but what are your thoughts about that?
Yeah, scientists advising government, it's a great concept. Now in Canada, we're actually really good at this. We have some fantastic leaders in science who are advising, and Mona Nima is our science advisor, who's a biochemist, who's doing absolutely tremendous work. And so in Canada, we're actually pretty good. And this is why we do have a strategy for decarbonization. And other countries too are actually quite good at this. So, but I would say that a lot of politicians are bombarded with information, and it's very difficult to sift through all that information, especially when it might seem self-serving. So, and you know, case in point, I have a difficult time because here I am proposing to for research funding in an area that I've been actively involved in and passionate about. So, you know, there's some element that would seem that it's self-serving. So how do you sift all this away if you don't really know anything about it? I would strongly recommend people read up about climate change. Just Google. You get some great sites and great insights. And then get governments to do the same, because if that doesn't scare the pants off you, then I don't know what will. We've seen some great movement all around the world with recognition of this problem. So scientists do advise governments, but as someone wrote in the chat, often governments have a small 3-4 year mandate, and that's not quite being that's not being fair to politicians, of course, because many of them have long-term visions. But we do have to make this. Impinge this urgency onto them now, so that we can start to work on it.
It's interesting. You know, it's coming. I mean, this political element's coming up a lot in the questions. There's a question from about what role do you see for government legislation and regulation in creating stricter controls and encouraging low carbon energy solutions? I mean, are there particular things you'd like to see starting to happen?
I'm going to say that is way out of my pay grade. So we have experts at SFU who spend their whole life about looking at policy and legislation and carbon taxes, and I would prefer to talk about things I really know about. And you know, you can speculate, but I wouldn't, just because I know a few words here and there about something that doesn't mean they're true. So I'm going to defer on that.
Thanks for your humility on this. I appreciate it. It's interesting, though. I'm curious. Have you spent time at all in terms of trying to engage with politicians and helping them to understand the potential of fuel cell technology? For example,
that's a good question. I engage in the Canadian Hydrogen Fuel Cell Association on the board. And there are people there that are very skilled and very knowledgeable when it comes to the socioeconomics of making a case for hydrogen, because that's where it comes down. I would say most government agencies do not want to hear about ion transport in plastics and how it's going to change the world. They do want to hear how it's going to put jobs and meals on the table and health and welfare. And so there are people around that board who are extremely effective and at presenting this information. Just go to the previous speaker. They talk about hydrogen in the steam reform, methane and steel and cement and the big picture with the big companies. So it is done absolutely. Where my involvement is often at the research level with places like the Canadian Hydrogen Fuel Cell Association, with government agencies that fund basic research, and mainly spend a lot of time trying to push the technology forward, because it's very, very time consuming. The minutiae of following and tracking science and working with students who are coming up with new discoveries all the time.
Yeah, it's challenging. You got to kind of figure out your lane and where you can make the biggest contribution. So I appreciate that. That's great. Connor Brady has his hand up.
Hello, yes, thank you for the second round of questions. This one is just, maybe you can debunk this myth or confirm it, but there's a common saying, at least that I've heard, that the energy going into recycling is actually more wasteful than not doing it at all. Is that?
Well, probably good question. So yeah, there's energy that goes into making plastics in the first place. That's energy and so on. There's certainly energy involved with collecting it and energy going into recycling it. So I don't think we can get to a circular plastics economy by simply recycling, collecting, sifting through. We can't get that. You can't differentiate a lot of the plastics easily. You may have noticed, to the best of my knowledge, and again, I'm not an expert in recycling, around here, we can't put grocery bags in our blue bins for recycling, because grocery bags are not easily processed. They simply melt and will clog up all the gears and so on that go into revamping that material. So what I was trying to touch on, again, looking at the future, 2030, 2040, is not really that we need to do recycling better and everybody has to do their bit better, which we surely do. But the plastics industry has to rethink what it does with plastics. For instance, can it make new versions of plastics which they can collect and then treat with a catalyst or pressurize and falls back into their original monomer components? For instance, polyethylene terephthalate, PET bottles, they've got groups in there that can cleave and you can get back the monomers. So there are companies now that are developing catalysts and technologies to reclaim that and get back the original organic stuff from where it came. That's the kind of mentality we want and try to develop. And that costs money, because plastics industry is very tight in terms of the cost benefit. Its profit margins are very small. So any small increases in plastic costs really come down and affect the bottom line. So government subsidies to move to more recyclable polymers or plastics, polymers with tags in them, infrared tags that you could easily, means you can extract, recycle. really new ideas in the way we think about commodity plastics. That's what I'd like to, that excites me and propose. Yeah, that's where I'll leave that.
We're running out of time and I see more questions coming. I'm going to take the last one from Dan, though, and with apologies to people who have questions still sitting in the chat. Dan, Lance.
Thank you very much, Dr. Holdcroft, for your presentation. It was very interesting. I'm gonna come out straight out. I run the recycling program for the province of British Columbia. All plastics in British Columbia are recycled every single day. We can recycle number 1, 2, 4, 5, 7, and all of the plastic films. And so it is not a problem with capturing them. They go through depots for the plastic films. And all of the other containers all go through a recycling system that is more than robust and is capturing well over 95% of everything we take in through the blue box and the cart systems across the province. And I've been doing that for a number of years.
Well, thank you for sharing that. And I will certainly follow up with that. That's great. Yeah.
Yeah, Dan, thanks for that intervention.
Thank
People
you.
have been asking about that. That's fantastic. Really
I have been
appreciate it.
chatting through the chat box all night telling people. So
That's
it's been
great.
Thank you.
Thank you so much. That's great. Listen, everyone, I'm sorry we're out of time. There are all sorts of very interesting questions still in the chat, so I will make sure that they get sent over to you, Steve. I want to thank you ever so much for a great, fascinating lecture. Obviously, from what you see in the chat, people are really interested. They're really interested in the political elements in particular, how we drive change. I think we're all feeling the urgency of this issue, and you really helped us see that there are scientific solutions that can assist us. So I really appreciate you spending time with us this evening. It does take a village to put together an event like this, and I want to thank the excellent captioners from AI Media who have helped us with the closed captioning. Public Square, always a delight to work with. They do outstanding event organization, so thanks to Public Square. You bring us together, you help us learn and engage with each other, and I'm very, very deeply appreciative of that as well. Also want to just let everyone know that the next President's Faculty Lecture is going to take place on June the 1st at 6 p.m. It features Professor Kelly Lee. She's a professor at the Faculty of Health Sciences and a Canada Research Chair. And she's going to be presenting pandemics and borders, how to manage travel restrictions more effectively. So you can find out more about this and other upcoming events on the SFU Public Square website at SFU.ca/Public Square. So I think there's a little video to close us out with. So I'm going to pass it over to them. And I want to thank everyone for joining us this evening. It's really been a pleasure. Thanks again, Steve. That was great. Have a good evening, everyone.
Thank you.